Hey everyone, Morgan here. So we're going to pick up with our gas law lectures today, and we're going to talk about Jacques Charles. Now, Charles was a Frenchman, scientist, inventor, and is generally credited with being the first person to take up a hydrogen-filled balloon. And he did this in 1783 in Paris. He launched from what is currently the site of the Eiffel Tower, and it was a pretty major social event. They sold tickets. That was actually how he was supporting his research, was by selling tickets to watch the launch. And one of the people that was actually in attendance for this was Benjamin Franklin. He was in a diplomatic position in Paris at the time. And being an inventor himself, this was something he was highly interested in watching. Now, there's generally some misunderstanding thinking that Charles took up the first hot air balloon, but his was actually a hydrogen filled balloon. Okay? Now, Charles is given credit mostly by a guy that we're going to talk about a little bit later today with coming up with what we now call Charles' law, or that the volume and temperature of a gas are directly proportional, meaning that if you heat the gas, it is going to expand. Okay? That doesn't mean gas particles get bigger. Okay? What it means is that the distances between them get bigger because they're moving faster and pushing out more. Okay? Now, this is a graph, straight line graph. That's what, a direct proportion represents, unlike the one you did with Boyle's law. Now, you see a dotted line here where we have actually extrapolated this out a bit. And those were not measurements that were taken, okay? That's just following the trend of the line. And you'll see that it meets the origin there, the point 0, 0. And we'll talk about that more in a second. So the volume and temperature of a gas are directly proportional, or algebraically, volume over temperature equals a constant. Now, what that means is that we can do a two-point formula. V1 over T1 equals V2 over T2. And that can be solved algebraically. And that's a pretty important relationship for us. Now, to demonstrate what we're talking about, I'd actually be doing a whole bunch of demonstrations again today. So I've tried to capture some versions of them from YouTube. Not exactly how I would do them, but still close enough. So let's take a look at this one.
So as we've already talked about Charles' law, it states that there is a direct relationship between volume and temperature of a gas. So what we want to do is we want to show this direct relationship by decreasing the temperature of the gas in this balloon here. We're going to do that using liquid nitrogen. Liquid nitrogen at a temperature of negative 196 degrees Celsius will decrease the temperature of the gas in the balloon. Let's see what happens to volume. As you can see, the volume of the gas in the balloon decreased when temperature was also decreased. As the temperature of the balloon starts to increase back to its normal room temperature, you see that it goes back to the original volume.
Okay, now, what we're going to see at this point is kind of interesting. This graph shows you plots for the same gas, but actually done at 4 different pressures. And it's a volume versus temperature plot, and we hold the pressure constant for each of those lines. But you see that they are all converging on the same temperature, which is negative 273.15 degrees Celsius. And it's a plot like this that allows us to develop the idea of the Kelvin temperature scale. Now, we could do the same thing here for 4 or 5 different gases, and we would see the same thing happen. They all have the same y-intercept. Very commonly, we switch the scales. We put temperature on the y-axis and volume on the x, and that way we really see it as a y-intercept. But that temperature is now referred to as absolute zero. Okay? So absolute zero represents the temperature at which molecular motion stops. Now, it is misleading on this graph because it almost makes you think that the volume of the gas is going to be zero, and that is not possible. The atoms are still going to take up some space, but they take up so little space when they're in the solid form, that's what they turn into a solid at these temperatures, that we consider it to be a negligible volume. Okay? So we are, in a sense, kind of lying to you by saying that, this hits at 0, okay? If you do the temperature as Kelvin temperatures, they'll always have a little bit of volume, but it is so small compared to the volume that those particles take up in the gas phase that we really don't need to worry about it. So no colder temperature than this, okay? That allows us to establish the absolute scale. Basically, the molecules are going to stop moving. So if we want to calculate the Kelvin temperature of something, it equals degrees Celsius plus 273. Okay, so algebra-wise, what is the new volume of 10.0 liters of gas at 273 Kelvin is heated to 373 Kelvin? So that's going to be a V1 over T1 equals V2 over T2. Now, one way of approaching this is just to plug the numbers straight in and leave an X or a question mark for what we don't know, and then to solve for that unknown. This would be 13.7 liters. And this is something that you need to pay attention to, sig figs, when you do this. Okay, sig figs are back to haunt us again. All right, second problem. We'll look for temperature this time. The algebra is perhaps a little bit more complicated. It's still very doable. There's only one unknown. 137 Kelvin. There'll be plenty of this that happens in your Charles Law homework. Okay, so can we combine the idea of Boyle's Law and Charles' Law, put them together? The answer is yes, and it's actually called the combined gas law. P1 V1 divided by T1 equals P2 V2 divided by T2. So algebra, there's more to do. There's 6 terms rather than 4, okay? But it really isn't any harder because you're still just dealing with one variable. Okay, so the person I was alluding to earlier that gave credit to Charles for his experiments was Joseph Gay-Lussac. There's a great stamp from France that features him. Now, Gay-Lussac, we give credit to today for coming up with the idea that temperature and pressure are directly proportional. Now, he published Charles' Law first, and he cited in it some unpublished research that Charles had done. But it's pretty generally considered that Gay-Lussac was really the genius here, and that Charles was just kind of riding on his coattails. So he saw a direct relationship between pressure and temperature. If you heat a gas up, the particles start moving around faster. Now, if that's in a balloon, great. The balloon gets bigger, the balloon gets smaller when you cool it off. But what if it's in a container that has a fixed volume? It means that the particles are going to hit the walls of the container more often and harder, and the pressure is going to go up. So P over T is equal to a constant, or in terms of a 2-point formula, we can say P1 over T1 equals P2 over T2. Now this is something we can actually demonstrate pretty easily. So we're looking at a soda can here. Now that soda can is empty. We've taken the soda out and put in just a small amount of water. Now there is air in that can. There's air outside that can. The pressures are balanced because the can is open. Now if you boil the water, it pushes the air out of the can. And the water vapor is going to be in the can at a pressure equal to the pressure outside the can. So particles are pointing out, pushing out. Particles are pushing in. On the inside of the can, it's water particles pushing out. On the outside, it's nitrogen and oxygen pushing in. Okay? And the gas leaves the can until the two pressures are exactly the same. So let's watch this.
This is a really fun demonstration that can easily be done as a student activities. Students love to do this as an activity. It provides an effective introduction to atmospheric pressure. To get started, you'll need some pop cans. You'll need a striker and a Bunsen burner, a little bit of water, some tongs, and a large container of cool water. Pour about 20 milliliters of water into the can, get the burner started, and then hold the can over the burner to cause the water to boil. The purpose of the water is we want the water to change to steam, and that forces the air out of the can. You'll know that it's ready to go as soon as you see the fog or the cloud form outside the opening of the can. Then in one smooth motion, invert the can into the cool water. What's happening here is right now you have the can filled with steam, that is hot water vapor. The air has been forced out. Then as the opening of the can is submerged, the steam starts to condense. So there is less gas pressure inside pushing out against the atmosphere, and the atmosphere crushes the can. To print out instructions and suggestions, go to montanascience.org and select lesson plans. To see other videos that I have produced, type in my name, Rod Benson, into the search window at teachertube.com.
Okay, so let's talk about what was going on. The can is turned upside down. You stick it in the cold water. Now, because it is submerged, so to speak, the opening does not allow any air to get in. The water vapor cools rapidly, turns back into a liquid. So it's not pushing out anymore. In essence, what you've created inside that can is a vacuum. Now, on the outside, air is pushing in. But it's not a balanced force. There's nothing pushing back out. So the can is going to be crushed. Now, it only works if you invert the can. Because if you put it in with that opening pointed up, air can rush into the can and the forces stay balanced. Now, my friend Tom Kunzelman, who teaches in Michigan, he did this very slow speed video of what's happening to the can. So take a look at it. All right, so things to note. We'll watch this one again so that you can see it better. When he gets it upside down, a little bit of boiling water comes out. Okay, so there was still a little liquid water in there, along with all of the steam, which, the water vapor. Now, as the can gets crushed, water from the beaker can actually run back into the can. It gets pushed up into the can as if this were like a barometer. So if there had actually been video of it pulling the can back out, you'd see a whole lot of water drop out. Now you're also going to see that it doesn't happen instantly. It takes half a second or so for that water to condense, the water vapor to condense, and to bring the pressure in that can down to basically zero. Takes a second, and then crush. Boom. Okay, so let's look at a problem related to that. What is the new pressure if a gas at 273 Kelvin exerts 1 atmosphere, is heated to 373 Kelvin? So that's a P1 over T1 equals P2 over T2. Plug your numbers in. Pretty straightforward algebra. You'll be multiplying both sides by 373 Kelvin. You get P2 equals 1.37 atmospheres. Does that make sense? Well, what has happened? We have increased the temperature, which means the particles are flying around more and more, okay? And they're going to push out harder on the walls of the container. The pressure should go up. Now let's look at this one, which is actually a combined gas law problem. What is the new volume of 15.0 liters of gas at STP is heated to 373 Kelvin and 0.5 atmospheres? P1V1 over T1 is equal to P2V2 over T2. So that's your setup. There's a little more arithmetic. And we get a V2 of 41 liters. Okay, that's it for today's lecture. All right, hope you're having a good day, and we will see you all again next time. This is Morgan signing off.